The night of November 7th, 1942, Richmond, California. Midnight approached. In Permanente Metals, Corporation Yard Number 2, a foreman named Bill Reed checked his watch for the third time in as many minutes. Around him, the shipyard hummed with a tension that had nothing to do with the war raging across two oceans. This was different. This was personal. On the ways before him sat an empty foundation, just steel beams marking where a ship would be. In 72 hours, if everything went according to plan, a complete Liberty ship would stand in its place. Ready to launch. Ready for war. 72 hours. The old-timers from the East Coast shipyards had laughed when they heard. You can't build a ship in 3 days, they said. It takes 6 months, maybe 8. That's how it's always been done. That's how ships are built. But Henry Kaiser, the man who'd never built a ship in his life before 1940, didn't care how things had always been done. And in 60 seconds, when the clock struck midnight and the keel for Hull 440 was officially laid, Reed and his crew were about to prove that everything the shipbuilding industry knew was wrong. The clock hit 12:01. Reed raised his hand. Across the yard, a whistle blew. And the impossible began. This is the story of how one man's refusal to accept the word impossible transformed American shipbuilding, won World War II, and proved that sometimes the best person to solve a problem is someone who doesn't know it can't be solved. This is the story of the Liberty ships, and it starts not with ships, but with a radical idea about metal, fire, and the fundamental nature of how things are joined together. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand what happened that November night, we need to go back 2 years earlier, to a moment when the world was burning and America hadn't yet decided to fight. December 1940. Britain was alone. France had fallen. The Soviet Union had signed a non-aggression pact with Hitler. The United States was still officially neutral, but everyone knew it was only a matter of time, and Britain was drowning, not metaphorically, literally. German U-boats prowled the Atlantic, hunting merchant ships carrying food, fuel, medicine, ammunition, the lifeblood of a nation at war. The mathematics were brutal and simple. Britain was losing ships faster than it could build them. 3 sunk for every one launched. At that rate, the island nation would be starved into submission before 1941 ended. Churchill knew it. Roosevelt knew it. And into this crisis stepped an unlikely figure. Henry John Kaiser, age 58, builder of dams and bridges, a man whose entire experience with ships consisted of once taking a ferry across San Francisco Bay. The U.S. Maritime Commission, desperate for anyone who could produce vessels quickly, offered Kaiser a contract, build 30 cargo ships for Britain. The commission expected him to politely decline. He had no shipyards, no trained workers, no expertise. Kaiser said yes. The traditional shipbuilding companies were appalled. One executive from Bethlehem Steel said, "Kaiser is a dam builder. Ships float, dams don't. He'll fail within 6 months and we'll have to clean up his mess." Another said, "The man doesn't even know how to read a ship's blueprint." Both statements were true. But Kaiser had something more valuable than experience. He had a completely fresh perspective. When the Maritime Commission showed him how ships were built, the months-long process of constructing from the keel up, one crew, one ship, using techniques perfected over centuries, Kaiser's response was immediate. "That's insane. That's not building. That's crafting. You can't craft your way out of this war." Traditional shipbuilding in 1940 was an art form passed down through generations, master shipwrights, trained apprentices for years. The process was slow, methodical, precise. You started with the keel, the spine of the ship, laid in a massive wooden cradle called the ways. Then you built the ribs, the curved steel frames that gave the ship its shape. Each rib was individually fitted, positioned, and secured. Then came the hull plating, sheets of steel carefully measured, heated to make them pliable, positioned against the frame, and secured. And here was the bottleneck, the eternal, immovable bottleneck. Rivets, Each steel plate was joined to the frame and to adjacent plates by rivets, thousands of them, tens of thousands. A Liberty ship required over 1 million rivets, and riveting was not a process you could rush. A riveting team consisted of 4 men. The heater worked a portable forge, heating rivets until they glowed orange-white, around 1800 degrees Fahrenheit, at exactly the right temperature. The heater would use tongs to toss the rivet through the air to the catcher, who would snag it, often barehanded using a leather pad, and immediately insert it through aligned holes in the steel plates. The bucker, positioned on one side of the hull, would hold a massive hammer, called a dolly bar, against the rivet head. The riveter, on the other side, would use a pneumatic hammer to pound the hot rivet's tail flat, creating a permanent joint. This had to happen in seconds. Wait too long, and the rivet cooled. Cool rivets didn't flatten properly, creating weak joints. A good team could place maybe 200 rivets in an 8-hour shift. Do the math. 1 million rivets, 200 per day per team. Even with dozens of teams working simultaneously, it took months, and every riveter was highly skilled. 6 months of training, minimum. Some took a year. You couldn't just hire people off the street and teach them to rivet. It required strength, coordination, experience, and a tolerance for working on scaffolding. 60 feet in the air while red-hot metal flew past your head, Kaiser watched a demonstration at a traditional shipyard, studied the process, talked to the workers. Then he called a meeting with his engineers and said 4 words that would change everything. "We're not using rivets." The engineers thought he was joking. One of them, a man named Steve Bechtel, who would later become a construction magnate himself, pointed out the obvious. "Henry, rivets are how ships are built. Every ship in the US Navy uses rivets. Every merchant ship in the British fleet uses rivets. The technology works. It's proven." Kaiser's response was simple. "It's too slow, and we can't train riveters fast enough. How long to train a good riveter?" 6 months. Bechtel admitted. "We don't have 6 months. We barely have 6 weeks. What else can we use?" The answer came from an unexpected source. One of Kaiser's associates had recently visited a Ford automobile assembly plant in Detroit. He'd watched as workers used welding torches to join car body panels. It was fast, it was clean, and most importantly, it required minimal training. An experienced welder could train someone new in 2 weeks. Welding had been around since the late 19th century, but it was primarily used for repairs, not construction. Building an entire ship from welded joints, that was radical, possibly reckless. Welding created continuous seams. Riveting created distinct attachment points. If a weld failed catastrophically, it could propagate across the entire hull. If a rivet failed, only that single joint was compromised. Traditional shipbuilders had experimented with welding. They'd concluded it was too risky for large vessels. The joints weren't as strong as rivets. The welds were susceptible to corrosion. And most damningly, no one had successfully built a large ocean-going ship using primarily welded construction. It was unproven technology for high-stakes applications. Kaiser didn't care. He sent his engineers to study welding techniques used in pressure vessel construction, in pipeline laying, in steel frame building construction. They studied metallurgy, learned about heat-affected zones and stress concentration. They developed quality control procedures. They designed welding jigs that could hold steel plates in perfect alignment. And in March 1941, Kaiser broke ground on his first shipyard. The location was Richmond, California, a small city on San Francisco Bay. 6 months earlier, the site had been marshalled. Kaiser built it from nothing. Fabrication shops, crane systems, ways for assembling ships. But the most radical feature was invisible. It was the production philosophy. Kaiser didn't build a shipyard. He built a ship factory. Instead of constructing vessels from the keel up on the ways, he created a modular assembly system borrowed directly from automobile manufacturing. Separate fabrication shops would build complete sections of the ship: a bow module, a stern module, engine room sections with machinery already installed, deck sections with railings welded in place. These modules, some weighing 250 tons, would be moved to the ways on railroad flat cars and lifted into position by massive cranes. Workers would then weld the modules together. The entire ship was essentially a three-dimensional puzzle that could be assembled in a fraction of the time traditional methods required. But the real genius was in the parallelization. While one ship was being assembled on the ways, dozens more were being constructed simultaneously as separate modules throughout the yard. The first Liberty ship built using this method was the SS Patrick Henry, launched on September 27, 1941. Construction time from keel to launch, 244 days. The traditionalists crowed. "See, Kaiser's methods don't work. That's not much better than conventional building." But Kaiser was just getting started. His engineers analyzed every minute of the construction process. Where were the delays? Where were the bottlenecks? Which operations could be done simultaneously instead of sequentially? They redesigned the module construction sequence. They improved welding procedures. They trained workers in specialized repetitive tasks instead of trying to create generalists. Like Henry Ford building Model Ts, each worker became expert at one small part of the process. The second ship took 190 days. The third took 120. By early 1942, as America entered the war after Pearl Harbor, Kaiser's average construction time had dropped to 70 days per ship, then 60, then 50. The Maritime Commission watched in astonishment. The traditional shipbuilding companies watched in growing alarm. Their methods, refined over generations, were being rendered obsolete by a man who'd never built a ship until 2 years ago. But Kaiser's revolution created an unexpected crisis, a labor crisis. Building ships faster meant needing more workers, but skilled workers were being drafted into military service. The traditional pool of male shipyard labor was evaporating. Kaiser needed thousands of new workers, and he needed them immediately. So he did something that shocked industrial America. He hired women. In 1942, heavy industry was almost exclusively male. Women worked in textile factories, in clerical jobs, in nursing. But shipyards, welding, operating cranes, that was men's work. Too physically demanding, too dangerous, too technical. Kaiser didn't care about convention. He needed workers who could be trained quickly. And welding, unlike riveting, didn't require exceptional physical strength. It required steady hands, good hand-eye coordination, and attention to detail. Women could do this. In fact, some of Kaiser's trainers quietly admitted that women often made better welders than men. They were more patient, more precise, more willing to follow exact procedures. The recruitment was massive. Advertisements ran in newspapers across the West Coast. Women needed for defense work. No experience necessary. We'll train. They came by the thousands. Housewives from Oakland, waitresses from San Francisco, teachers from Sacramento, farm girls from the Central Valley, women whose husbands, sons and brothers were fighting overseas and who wanted to contribute to victory. The training program Kaiser developed was ruthlessly efficient. 2 weeks. That's all the time new welders got. First 3 days. Theory. How welding works. Different types of welds. How to identify good welds versus bad ones. Days 4 through 14. Hands-on training with scrap metal. Progressing to actual ship components. By the end of 2 weeks, a woman who'd never held a welding torch was certified to work on actual ships. The quality control was strict. Every weld was inspected. X-rays checked for internal flaws. Pressure tests verified integrity. Any worker whose welds consistently failed inspection was retrained or reassigned. The system worked because it had to work. These ships would carry soldiers into combat. They would transport ammunition, fuel, medical supplies. A failed weld could mean a ship breaking apart in the North Atlantic, drowning everyone aboard. By mid-1942, women comprised 30% of Kaiser's shipyard workforce. The government created recruitment posters featuring Wendy the Welder, though she never achieved the iconic status of Rosie the Riveter. Perhaps welding lacked the romance of riveting. Perhaps the sexism of the era couldn't fully accept women doing such technical work. But the Wendy's built ships, hundreds of them. One woman, a former secretary named Margaret, later recalled her experience. I'd never even held a tool before the war. My husband taught history at Berkeley. I taught piano lessons. Then Pearl Harbor happened, and suddenly there was this ad in the paper. Help build ships. Help win the war. I thought, why not? 2 weeks later, I was welding hull plates on a Liberty ship. I was terrified the first few times. What if I did it wrong? What if my weld failed and the ship sank? But the supervisors were patient. They taught us, and after a while, you got confident. You knew what a good weld looked like, felt like, sounded like. I worked at Kaiser for 3 years. I welded on 87 ships. 87. When I see newsreels from the war, ships at Normandy, ships in the Pacific, I think, maybe I worked on that one. Maybe my welds helped bring our boys home. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By September 1942, Kaiser's yards were producing ships at an average rate of 45 days from keel to launch. The Maritime Commission was ecstatic. Britain was grateful. And then Kaiser decided to prove what was truly possible. At his Oregon Shipbuilding Corporation yard in Portland, his team set a new record. The SS Joseph N. Teal completed in 10 days, from start to finish. The shipbuilding world declared it impossible, a fluke, a stunt. A reporter asked Kaiser if it could be done even faster. Kaiser, never one to back down from a challenge, smiled and said, "Watch." 2 months later, in November 1942, came the Robert E. Peary. Kaiser's Richmond Yard No. 2 had been preparing for weeks. Every module was pre-built to exact specifications. The engine room section arrived with all machinery installed and tested. The deck sections came with railings, ventilation systems, and electrical conduits already in place. The bow and stern assemblies were complete units. When the clock struck midnight on November 8th and the keel was officially laid, workers were ready with a level of coordination that resembled a choreographed performance. The first 12 hours saw the bottom shell and inner bottom sections welded into place. The boilers, massive steel units weighing tons, were lowered into position by mid-morning of the first day. By nightfall, the basic hull structure was complete. The second day brought the upper deck sections, bulkheads, and the stern structure. Workers moved with practiced efficiency, each person knowing exactly what came next. The welding crews worked in shifts around the clock. One team would complete a section, inspect it, and immediately move to the next, while another team took over the finished work for final checks. The third day saw the superstructure rise. The bridge, the mast, the cargo derricks. Everything was modular, everything pre-built, everything designed to fit together with minimal adjustment. By the evening of day 3, the Peary looked like a complete ship. The fourth day was finishing work. Final welds, painting, installation of defensive armament, the gun platforms that would hold anti-aircraft weapons, and a stern-mounted deck gun. Electrical systems were tested, the propeller shaft was aligned, the ship was made ready for sea. On November 12th, 1942, at 3:27 in the afternoon, Mrs. Charles Cushing smashed a bottle of champagne against the bow of the SS Robert E. Peary. The ship slid down the ways into San Francisco Bay. Construction time, from keel laying to launch, 4 days, 15 hours, and 29 minutes, 250,000 individual parts, 14 million pounds of steel, one complete Liberty ship. The previous record had been 10 days. Kaiser had cut it in half. Newsreels played in theaters across America. The ship that was built in 4 days. Newspapers ran headlines declaring Kaiser a miracle worker. The British Admiralty sent an official letter of congratulation. Stalin, not normally given to praising capitalist achievements, remarked that American industrial capacity was astounding. But the experts were quick to point out that the Peary was a publicity stunt. Kaiser himself called it an incentive ship, meant to boost worker morale and demonstrate what was possible under ideal conditions. You couldn't sustain that pace. There wasn't enough steel, there weren't enough cranes. The normal production rate at Kaiser's yards was 45 to 50 days, not 4, but that missed the point. The point wasn't that every ship could be built in 4 days. The point was that the old way of shipbuilding, the way that took 6 to 8 months, was obsolete. Kaiser had proven that modular construction and welding could reduce shipbuilding time by a factor of 5 or more. That was the revolution, not the speed record, but the complete transformation of how ships were built. By 1943, Kaiser's yards were running at full capacity, 97,000 workers across 7 shipyards. The Richmond yards alone employed 45,000 people. At peak production, Kaiser's organization was completing 1 ship every single day, not 1 ship per yard per day. 1 ship per day, total across all yards. But the sheer volume meant that on some days, multiple launches would occur simultaneously at different facilities. The scale was unprecedented in human history. Between 1941 and 1945, 18 American shipyards built 2,710 Liberty ships. Kaiser's yards built 747 of them, 27% of the total. Add in the other vessels Kaiser produced, escort carriers, tankers, landing ship tanks, and his total contribution was 1,490 ships. One company started from nothing in December 1940, built 30% of America's wartime merchant fleet. The numbers tell a story of industrial mobilization that defies comprehension. Each Liberty ship cost approximately $2 million, the equivalent of about 30 million in today's currency. That seems expensive until you consider what they carried. A single Liberty ship could transport 2,840 jeeps, or 440 tanks, or 230 million rounds of rifle ammunition. They could carry locomotives on their decks. They could carry entire hospitals, disassembled, ready to be rebuilt on invasion beaches. But behind every statistic was a human story, like the woman we know only as Worker 738 in Kaiser's employment records. She was a welder who specialized in the double bottom, the space between the outer hull and the inner bottom floor of the ship. This was claustrophobic work. The space was sometimes less than 2 feet high. Workers had to slide in on their backs, welding torches in hand, working in near darkness, the only light coming from the torch itself. This woman welded for 3 years. 8 hours a day, 6 days a week, sometimes 7. She welded seams, joints, patches, reinforcements. By one calculation, she welded over 800 miles of seam joints during her time at Kaiser. 800 miles, the distance from San Francisco to Denver, all of it done lying on her back in darkness, breathing metal fumes, creating joints that had to be perfect because lives depended on them. She was never famous. No newspaper interviewed her. No newsreel camera captured her at work. But her welds held. Through storms in the North Atlantic, through attacks by U-boats and aircraft, through 4 years of global war, her work held. She retired in 1945 when the war ended, returned to her pre-war job as a seamstress, and died in 1983. Her obituary made no mention of the ships she'd built or the lives she'd saved. But they existed nonetheless. The Liberty ships themselves were decidedly unglamorous. 441 feet long, 57 feet wide, with a boxy, utilitarian profile that earned them the nickname Ugly Ducklings. President Roosevelt, himself a former Assistant Secretary of the Navy and an enthusiast of elegant ship design, called them dreadful-looking objects. The Maritime Commission tried to counter the negative publicity by hosting a grand christening ceremony for the first 14 ships, during which Roosevelt gave a speech invoking Patrick Henry's "Give me liberty or give me death," thus coining the name Liberty Ship. But ugly or not, they worked. They were powered by old-fashioned reciprocating steam engines, the same basic technology used since the late 19th century. Modern ships use diesel engines or steam turbines, but Kaiser deliberately chose obsolete technology. Why? Because multiple manufacturers could build reciprocating engines, because spare parts were readily available, because every merchant marine engineer knew how to maintain them. The Liberty ship wasn't meant to be sophisticated. It was meant to be buildable, maintainable, and above all, reproducible in massive quantities. The ships had a design cruising speed of 11 knots, barely 13 miles per hour, slow by any standard. But speed wasn't the priority. Capacity was. Each Liberty ship could carry 9,000 tons of cargo in its 5 holds, and the deck could accommodate additional cargo secured with chains. They carried the materials of war: steel for building tanks, aviation fuel for bombers, penicillin for field hospitals, K-rations for soldiers, ammunition for artillery, the unglamorous logistics that actually win wars. But in 1943, a crisis emerged that threatened to destroy confidence in the entire Liberty ship program. Ships were failing, not sinking in combat, failing structurally. Liberty ships sailing through the North Atlantic were developing cracks in their hulls. Small fissures would appear around hatches or along weld seams, then propagate rapidly through the steel. Some ships limped into port with cracks dozens of feet long. Others weren't so lucky. On November 24, 1943, the SS John P. Gaines broke completely in, half in the North Pacific. The ship was sailing in moderately rough seas, nothing extreme, when the hull suddenly split just aft of the midship. The stern section sank within minutes, taking 10 crew members with it. The bow section stayed afloat long enough for the remaining crew to be rescued, but the incident sent shockwaves through the Maritime Commission. Then it happened again. The SS Schenectady, a tanker built using similar welded construction techniques, broke in half while moored in calm water in Portland, Oregon. The ship wasn't even loaded with cargo. It wasn't under stress from waves or weather. It simply cracked down the middle while tied to the dock. Then the SS Esso Manhattan split in two in New York Harbor. By early 1944, 12 ships had broken completely in half, and nearly 1,500 had reported significant structural cracks. The Maritime Commission launched urgent investigations. Was the welding faulty? Were Kaiser's workers, trained in just 2 weeks, making critical mistakes? Had the rush to build ships quickly compromised structural integrity? Traditional shipbuilders who'd warned against welding now pointed to the failures as proof they'd been right all along. "We told you," they said. "Welded ships are inherently weak. This is what happens when you ignore centuries of proven shipbuilding practice." Kaiser faced a potential catastrophe if confidence in Liberty ships collapsed, if the Navy refused to load them with troops, if the Maritime Commission halted production while lengthy investigations were conducted. The entire war effort could be jeopardized. The timing couldn't have been worse. D-Day was being planned. The invasion of Europe would require thousands of ships to transport hundreds of thousands of troops. If Liberty ships couldn't be trusted, where would those ships come from? The investigation initially focused on welding quality. Inspectors examined failed welds, looking for flaws, porosity, incomplete fusion, anything that might explain why ships were breaking apart. But here's what puzzled everyone. Most of the cracks didn't originate at welds. They started at square corners of hatches, at stress concentration points in the hull design, at places where the steel itself was failing, not the joints between steel plates. The answer came from an unlikely source: Constance Tipper, a British metallurgist working at Cambridge University. Tipper had spent the early war years studying metal fracture mechanics, particularly in aircraft components. When news of the Liberty ship failures reached Britain, she requested permission to examine a ship. The British Ministry of War Transport lent her the Empire Duke, a merchant vessel built using similar construction techniques. Tipper subjected sample plates from the Empire Duke to various temperature and stress conditions. What she discovered revolutionized materials science. Steel, she found, has a critical temperature point called the ductile brittle transition temperature. Above this temperature, steel is ductile, meaning it bends and deforms under stress. Below this temperature, steel becomes brittle, meaning it fractures rather than bends. The steel used in Liberty ships had a transition temperature around 40 degrees Fahrenheit. In warm water, the Mediterranean or the Pacific in summer, the steel remained ductile. Ships could flex with waves, absorb stress, bend without breaking. But in the North Atlantic, During winter, when water temperatures dropped to near freezing and air temperatures went well below zero, the steel became brittle. A small crack, perhaps started by a stress concentration at a square hatch corner, could propagate rapidly through brittle steel. But this didn't explain why riveted ships sailing in the same cold waters didn't experience the same catastrophic failures. Tipper discovered the answer through brilliant deductive reasoning. Riveted construction created natural crack arresters. Each steel plate was separate, joined to adjacent plates, only at discrete rivet points. If a crack formed in one plate and reached a rivet line, it couldn't easily jump to the next plate. The separate plates, connected but not continuous, prevented crack propagation. Welded construction created a continuous sheet of steel. A crack could propagate unimpeded across multiple sections, across entire hull sections, until something stopped it or the ship broke apart. The welding wasn't the problem. The steel was the problem. And welding, by creating continuous structures, made the problem catastrophic instead of manageable. The solution required multiple approaches. First, better steel. Metallurgists developed new alloys with lower transition temperatures, steel that remained ductile even in Arctic waters. Second, structural modifications. Engineers added crack arresters, reinforcement straps, and deliberately included some riveted seams at critical points to prevent crack propagation. Third, design changes. Square hatch corners, which created severe stress concentrations, were replaced with rounded corners. Fourth, operational changes. Liberty ships were routed through warmer waters whenever tactically feasible. The fixes worked. By late 1944, catastrophic structural failures had essentially stopped. The ships, modified with improved steel and structural reinforcements, proved reliable even in the worst North Atlantic winter storms. But the crisis had exposed something important. Kaiser's revolutionary methods had worked brilliantly for production speed, but they'd also revealed gaps in material science that no one had anticipated. Ironically, the Liberty ship failures became one of the most important contributions to engineering knowledge in the 20th century. The thousands of ships that experienced brittle fractures became case studies for understanding fracture mechanics. Graduate students in metallurgy and structural engineering would study Liberty ship failures for decades. The lessons learned led directly to modern fracture toughness testing, to better steel formulations, to improved welding procedures, to fundamental changes in how engineers think about structural design. Ships today avoid sharp corners specifically because of Liberty ship failures. Modern steels are tested for fracture toughness at various temperatures. Welders receive extensive training in techniques that minimize stress concentration. Structures are designed with crack propagation paths in mind. All of this came from studying what went wrong with the Liberty ships. The failures, tragic as they were, advanced engineering knowledge by decades. But for every ship that failed, dozens performed magnificently. Liberty ships carried 2/3 of all American cargo during World War II. They were the lifeline that kept the Allied war effort functioning. Without them, D-Day couldn't have happened. The invasion required 7,000 ships to transport 150,000 troops and their equipment across the English Channel. Liberty ships carried the tanks, the ammunition, the fuel, the food. They carried the material weight of an entire invasion force. One Liberty ship, the SS Stephen Hopkins, earned legendary status. On September 27, 1942, the Hopkins was sailing alone in the South Atlantic when it encountered two German ships, the auxiliary cruiser Stier and the blockade runner Tannenfels. The German ships were heavily armed raiders, disguised as merchant vessels but carrying torpedo tubes and artillery. The Hopkins had a single 4-inch deck gun and a few anti-aircraft weapons. It was outgunned, outmanned, and had no chance of survival in a straight fight. The captain, Paul Buck, could have surrendered. Instead, he gave the order to fight. The Hopkins's gun crew, civilian merchant mariners, engaged both German ships. The Steyer's superior firepower quickly tore into the Hopkins, but not before the American gun crew scored critical hits on the Steyr, setting it on fire and disabling its steering. The Hopkins sank, taking most of its crew with it. But the Steyr, too damaged to continue, also sank. The Hopkins was the first American merchant ship to sink a German surface raider. Its crew, civilian volunteers who could have stayed safely home, fought a hopeless battle and took an enemy warship with them. One of the few survivors later said, "We knew we couldn't win, but we figured if we could hurt them bad enough, maybe the next convoy would be safer." After the war, Liberty ships continued service for decades. They carried supplies during the Berlin airlift, when Stalin blockaded West Berlin and the West responded with a massive aerial resupply operation. Liberty ships brought the cargo to ports where it was transferred to aircraft. They transported troops and equipment to Korea during that war. They served as merchant vessels throughout the 1950s and 60s, carrying commercial cargo around the world. The last Liberty ship in active commercial service wasn't retired until 1972, 30 years after the first one was built. The ships that critics called expendable, designed for maybe one or two crossings of the Atlantic, proved remarkably durable when properly maintained. Of the 2,710 built, about 200 were lost during the war to enemy action. The rest survived. Most were eventually scrapped, but not because they were worn out. They were scrapped because they'd become obsolete, replaced by faster, larger, more efficient vessels. Today, only two fully restored Liberty ships remain operational. The SS Jeremiah O'Brien, moored in San Francisco, and the SS John W. Brown in Baltimore. Both are museum ships that still sail occasionally, maintained by dedicated volunteers who want to preserve the memory of what these ships represented. Walking the decks of the O'Brien or the Brown, you can still smell the oil and metal, still see the cramped quarters where crews lived, still imagine what it was like to cross the Atlantic in winter knowing that German submarines were hunting you. The SS Robert E. Peary, the ship that started this story, had a distinguished war career. After its record-breaking construction and launch, the Peary sailed on November 22, 1942, carrying food and war supplies to Noumea, New Caledonia, a critical Allied base in the South Pacific. Over the next 3 years, the Peary made dozens of crossings of both the Atlantic and Pacific. It transported ammunition to Guadalcanal, carried troops to Normandy for D-Day, brought prisoners of war back from North Africa, delivered locomotives to Soviet ports via Murmansk on one voyage in the Pacific. The Peary performed an extraordinary rescue. American soldiers were trapped on a beach held by Japanese forces. The Peary maneuvered close to shore within range of Japanese artillery and used a line-throwing gun to shoot a rope to the beach. Over that rope, the crew rigged a pulley system and sent ammunition and food to the trapped soldiers, keeping them supplied until reinforcements arrived. The ship's armed guard crew, 17 Navy gunners assigned to protect the vessel, kept Japanese positions suppressed with anti-aircraft and deck gunfire. The Peary survived the war intact, continued merchant service for 18 more years, and was finally scrapped in Baltimore in 1963. 21 years of service. Not bad for a ship built in 4 days as a publicity stunt, but the real legacy of the Liberty ship program wasn't any individual vessel. It was the proof of concept. Kaiser had demonstrated that traditional manufacturing could be completely transformed by applying assembly line principles. After the war, those same principles spread to other industries. Housing construction adopted modular techniques, building wall sections in factories and assembling them on site. Aircraft manufacturing used jigs and fixtures developed for shipbuilding. Even computer hardware, decades later, would use modular design philosophies that traced their lineage back to Kaiser's shipyards. Kaiser himself became an American icon. He appeared on the cover of Time magazine. He was featured in dozens of Saturday Evening Post articles. Americans in a 1945 public poll named him the civilian who had done the most to help win the war. Ahead of even scientists who worked on the atomic bomb, there was serious talk of him running for president. He never did, choosing instead to build a post-war business empire. Kaiser Aluminum became a major producer of the metal that made modern aviation possible. Kaiser Steel challenged the dominance of East Coast steel manufacturers. Kaiser Motors built automobiles known for their safety innovations, including the first American car with a padded dashboard, and, perhaps most significantly, Kaiser Permanente started as a healthcare system for his shipyard workers, became one of America's largest health maintenance organizations, pioneering the concept of prepaid medical care. But ask Kaiser what he was most proud of, and he'd tell you about the ships. In a 1960 interview, 5 years before his death, Kaiser reflected on the Liberty ship program. "We built 1,700 ships," he said, getting the number slightly wrong in his old age. Most people remember the 4-day ship, but that's not what mattered. What mattered was the 15-year-old kid from Alabama who'd never seen the ocean, who came to work in our yards and learned to weld, the housewife from Oakland who thought she couldn't do technical work, then built ships that brought her husband home from Europe. We didn't just build ships, we proved that ordinary people, given the right tools and the right training, can do extraordinary things. The welding innovation that made the Liberty ships possible became standard practice in shipbuilding worldwide. Today, virtually all large ships are welded rather than riveted. The last major riveted ship built was probably in the early 1950s. Welding is faster, cheaper, lighter, and with modern techniques and materials just as strong as riveted construction. The problems that plagued early Liberty ships, the brittle fractures and crack propagation, were solved through better metallurgy and better design, not by abandoning welding. The modular construction techniques Kaiser pioneered are now universal. No shipyard builds vessels from the keel up with a single crew anymore. Every modern ship is built in sections, often in different countries, then brought together for final assembly. A cruise ship might have its engine room built in Finland, its superstructure built in Italy, and its hull assembled in France. That's Kaiser's legacy, the understanding that complex products can be built faster and better by breaking them into modules. But perhaps the most profound legacy was human. The Liberty ship program proved that in times of crisis, societies can mobilize in ways that seem impossible during peacetime. That ordinary people can learn complex skills quickly if the training is designed well. That women can do jobs traditionally reserved for men and often do them better. That hierarchical, tradition-bound industries can be transformed by outsiders who don't know the rules. When Henry Kaiser stood in that empty Richmond field in December 1940 and promised to revolutionize shipbuilding, he was making a bet, not just on technology or engineering, but on people. On the waitress who would become a welder, on the housewife who would become a crane operator, on the farmer who would become a pipe fitter. He bet that if you gave people the tools, the training, and a reason to care, they would accomplish miracles. And they did. Between 1941 and 1945, 97,000 workers in Kaiser's yards built 1,490 ships, 97,000 stories of transformation, 97,000 people who proved they were capable of more than they'd ever imagined. Some went back to their pre-war jobs when peace came. Others found that the war had changed them, that they couldn't go back to the way things were. They'd learned they could build ships. They'd learned they could do the impossible. That lesson, that ordinary people are capable of extraordinary things when necessity demands it, is perhaps more relevant now than ever. We face challenges today that seem insurmountable: climate change, pandemics, economic disruption. And it's easy to feel helpless, to think that problems are too big for individuals to solve. But the Liberty Ship program offers a different lesson. It says that when we face existential threats, when we mobilize our industrial capacity and our human creativity, when we're willing to ignore convention and try new approaches, we can build solutions at a scale that seemed impossible. Kaiser didn't solve the U-boat crisis by building better ships. He solved it by building more ships than the Germans could sink. Quantity produced with quality at a speed that overwhelmed the enemy. On that night of November 7th, 1942, when Bill Reed watched the clock tick toward midnight and prepared to lay the keel for the Robert E. Peary, he was nervous. The whole thing seemed crazy. Build a ship in 4 days, impossible. But Reed had learned something working for Kaiser. Impossible was just another word, for we haven't figured out how yet. At 12:01 a.m., the keel was laid. Workers swarmed the ways. Welding torches ignited, cranes lifted massive modules into position, and the impossible began. 4 days later, a ship slid into San Francisco Bay, a ship that would sail to 5 continents, that would carry supplies to Guadalcanal and Normandy and a dozen other battlefields, that would serve for 21 years and be part of the fleet that won the war and built the peace. The German U-boat commanders never understood what hit them. They sank Allied ships throughout 1942 and into 1943, confident that they were winning the Battle of the Atlantic. But every month, more American ships appeared. Many more, far more than the Germans were sinking. The mathematics had reversed. By late 1943, Liberty ships were being launched faster than U-boats could sink them. The tide had turned, and it turned because of welding, modular construction, and 97,000 workers who built the impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.